There's a sound in space that should not exist. Not because it's loud, not because it's distant, but because space is silent. There's no air, no medium, no way for sound to travel. That's one of the first principles of physics. Without particles to carry vibrations, sound simply cannot exist. And yet, something was recorded. This wasn't a rumor or a misinterpretation. The data came from deep space observations conducted by multiple research teams studying galaxy clusters, regions filled with massive structures, extreme gravity, and violent cosmic events. What they found wasn't visual. It was a pattern, a pressure wave embedded in hot gas surrounding a distant cluster, moving outward in a consistent, measurable rhythm. And when that data was converted into something humans could understand, it became a sound. That's where things start to break down. Because this wasn't just any signal. It wasn't random noise or background interference. The waveform showed structure, repetition, spacing, frequency. It behaved like something generated. Now, to be clear, this isn't sound in the traditional sense. No one heard it directly. What scientists detected were ripples in plasma, superheated, gas stretching across millions of light years. These ripples were caused by something powerful enough to push matter across unimaginable distances. And when those pressure variations were translated into audio frequencies, what emerged was a deep, resonant tone, lower than anything the human ear can naturally detect. In fact, it was measured at a frequency millions of times below our hearing range. But that's not the strange part. Because once the data was scaled, compressed, into a range we can hear, the result wasn't chaotic. It wasn't noise. It was consistent, almost like a sustained note. That shouldn't happen. Cosmic events are violent. Explosions, collisions, radiation bursts, they create turbulence, not harmony. Their signatures are messy, unpredictable. This wasn't. This was stable, continuous, and that raised the first serious question. What could possibly generate a signal like that, across such an enormous scale? The initial explanation pointed to a supermassive black hole at the center of the cluster. These objects are known to release enormous amounts of energy, often pushing out jets of matter and creating shockwaves in surrounding gas. That's expected, but the scale of this wave wasn't. It extended for hundreds of thousands of light years. The energy required to sustain it was beyond anything typically observed. And yet, the pattern held. That's when researchers began to analyze its structure more closely. They mapped the intervals, measured the amplitude, compared it to known astrophysical processes, and something didn't fit because instead of decaying naturally, as energy waves usually do, the signal appeared to maintain its form over distance. That's not how physics normally works. Waves lose energy. They dissipate. They fade. This didn't. This is where it gets uncomfortable. Because the deeper they looked, the more the signal resembled something intentional. Not in the sense of communication, not in any direct, provable way, but in its consistency, its persistence, its refusal to behave like noise. And then it got worse. A second analysis revealed subtle variations within the wave, tiny fluctuations embedded inside the larger pattern. At first, they were dismissed as interference, but they repeated, not randomly, not chaotically. In sequences. Now, no one is claiming. These sequences mean anything. Not officially, but they exist, and they don't match any known cosmic process. Which leads to a question scientists are still trying to avoid. If space is supposed to be silent, then what exactly are we listening to? By the time independent teams reviewed the data, the signal had already been verified. Different instruments, different methods, same result. A low-frequency wave, stretching across a galaxy cluster, behaving in a way no one could fully explain. At that point, the focus shifted, not to whether the signal was real, but to what it meant. Because once the existence of the wave was confirmed, a new layer of analysis began, one that went beyond detection and into interpretation. And that's where things start to break down. The original assumption was simple. A supermassive black hole generated the wave through periodic outbursts. These outbursts would push against surrounding gas, creating ripples, similar to dropping a stone into water. That model works up to a point, but when researchers aligned the timing of the wave with known activity from the black hole, the numbers didn't match. The intervals were off. The spacing between peaks didn't correspond to any observed cycle of energy release. In other words, the source wasn't behaving the way it should, but that's not the strange part. Because when they isolated the embedded fluctuations, the smaller variations within the larger wave, they found something even more unusual. The spacing wasn't random. It followed a pattern, not perfectly regular, not mechanical, but structured enough to stand out against natural noise. Now, in astrophysics, patterns can emerge from chaos. Turbulence can create temporary order. Statistical anomalies happen, but this persisted across multiple observations, across different datasets, and that raised a possibility no one wanted to prioritize, that the structure wasn't accidental. This is where it gets uncomfortable. Because if the smaller fluctuations are real, and if they're not caused by known physical processes, then the signal is doing something beyond simple propagation. It's carrying information, not necessarily a message, not necessarily anything. Intentional, but information nonetheless. And that introduces a problem. Because information implies encoding, and encoding implies a mechanism. So, what's the mechanism? Some researchers suggest interference patterns, multiple waves overlapping, to create the illusion of structure. Others point to gravitational distortions bending the signal in complex ways. These explanations are plausible. They fit within known physics, but they require very specific conditions. Conditions that, so far, haven't been confirmed in that region. And then it got worse. A recent reprocessing of the data using more advanced filtering techniques revealed that the signal isn't static over time. It's changing, slowly, subtly, but measurably. The frequency shifts, the amplitude adjusts. Not randomly, in response to something. Now, that could still be natural. External forces, environmental changes, unknown variables, but the adjustments appear coordinated, as if the system generating the wave is reacting, adapting. And that's where the uncertainty deepens, because adaptive behavior in a signal, on this scale, has no clear precedent, not in galaxy clusters, not in black hole dynamics, not anywhere we've observed before, which forces a new question, not what created the sound, but whether it's still being created. Right now, because if the signal is evolving, then whatever is producing it hasn't stopped. It's ongoing, active, and that changes the timeline completely. This isn't a relic from the distant past. It's something happening in real time, across millions of light years, and we're only detecting a fraction of it. That's where things start to break down again. Because the more precise the measurements become, the more unstable the explanations get. Every model accounts for part of the signal. None account for all of it. And the gaps aren't shrinking. They're growing, which leaves us with a situation that's difficult to frame, We've identified a wave in space that behaves like sound. We've translated it into something we can hear. We've analyzed its structure, its variations, its evolution. And still, we don't know what we're actually listening to. It doesn't behave like noise. It doesn't behave like a simple physical process. And it doesn't stay the same, which suggests one final possibility. That this isn't just a sound carried through space. It's a process unfolding within it. And whatever that process is, it hasn't finished yet.